Okay, in this lecture, we are going to learn about equilibrium of a particle. So in our previous lectures, I mentioned that particle is an object which has a mass, but the size can be neglected, right? If any object, if we can neglect its size or we can neglect its dimensions, but it has a mass, then we say it is a particle, right? At the same time, I mentioned that when we considering equilibrium, if any object, if we can ignore dimensions, when we write down the equilibrium equation, then we call it also a particle under mechanics, right? So in this lecture we are going to learn equilibrium of such type of objects, right? So first let's understand what is what does the term equilibrium means in mechanics, right? So equilibrium means in mechanics is, we say a particle is said to be in equilibrium if it remains, this is very important, okay, if it remains at rest. At rest means no motion, right? If it remains at rest, if originally at rest, if a particle is originally does not have any movement, then if it keeps doesn't have any movement, then we say a particle is in equilibrium. Not only that, has a constant velocity if originally in motion. In that condition, in that situation also, we say particle is in equilibrium, right? So in mechanics, equilibrium particle can, there are two types, right? If the particle is in equilibrium, if it's originally at rest and if remains and it remains at rest, then we say the particle is in equilibrium. Or if a particle is originally moving and it has a constant velocity, then we say the particle is also in equilibrium, right? So particle can be moving at a constant velocity, or it can be, it doesn't have any movement, then we say it is in equilibrium, right? So this is the condition for equilibrium. Actually, this is the condition for equilibrium, right? So to maintain equilibrium, it is necessary to satisfy Newton's first law of motion. What is the Newton's first law of motion? It tells an object will remain at rest or in uniform motion in a straight line unless acted upon by a external force, right? As long as there is no external force acted on the particle, it will remain at rest or moving at a constant velocity, right? So that is what Newton's first law. So it is necessary to satisfy Newton's first law to maintain the equilibrium. So which requires the resultant force acting on particle to be equal to 0, right? So if particle to be in equilibrium or to maintain equilibrium, the resultant force acting on the particle should be equal to 0, right? So this word is very important. Resultant force acting on the particle, right? Resultant force, not just forces. If you take particle, there can be forces like this, but the particle is still in equilibrium if the resultant force Fr is equal to 0, right? So so this is so this one is not only necessary condition for equilibrium, it is also a sufficient condition, right? If this condition satisfied, then we can say the particle is in equilibrium, right? So this follows from the Newton's second law of motion. We know that Newton's second law of motion, right? You all know it is F is equal to ma, right? So if the resultant force uh, since the force system satisfies, then ma should be equal to 0, right? We know that particle has a mass, so a should be equal to 0, right? So which means that particle acceleration is equal to 0, which means that either it should be at rest or it should moves with a constant velocity, right? Then we say it is the particle is in equilibrium, right? For us, what is important is that, so this is the condition need for the to maintain equilibrium, right? So this is the necessary condition for equilibrium. It's also the sufficient condition, as I mentioned. So if any particle to be in equilibrium, the resultant force acting on the particle should be equal to 0, right? So if you can see here, here is the bold letter, which means that the summation of vector summation of all the forces should be equal to 0, right? Resultant force Fr is equal to 0 means vector summation of all the forces on the particle should be equal to 0. Before moving with the equilibrium of particle, we will first consider three types of supports often encountered in particle equilibrium problems. First one is linearly elastic springs, right? So if a linearly elastic spring, or we say a cord of undeformed length L naught is used to support a particle, the length of the spring will change in direct proportion to the force F acting on it. A characteristic that define the elasticity of a spring is the spring constant, or we say stiffness, right? The magnitude of the force exerted on a linearly elastic spring which has a stiffness K and is deformed a distance S measured from its unloaded position is, we can use this equation, F equals to K times S, right? So elongated length, say after the force F, this is a spring extended its length to L, right? So elongated length S is equal to L minus L naught, right? So the force applied on this elastic spring at this moment is F is equal to spring constant of the spring constant of stiffness of this elastic spring times L minus L naught, or we can say Ks, right? For example, if Fs is positive causing an elongation, then F must pull on the spring, right? Whereas if S is negative, which means in this direction, say this is minus S, then this force is F must push the spring. Alright. So if we take for example, say if this is spring, uh, say stiffness constant of this spring is K is equal to 400. 400 we say Newton per meter, right? So this one tells how much force you need to elongate 1 meter of this spring, right? This Newton per meter, right? So this spring need 400 Newton to elongate 1 meter of the spring, right? So say the stiffness constant of this spring is 400, for example, right? So then uh, the original, the undeformed length, say L naught is equal to 0.8, and elongated length L is the deformed length L is equal to 1 meter. Then what is the force that required for this elongation? So F is equal to Ks, right? So K is 400 times S is 1 minus 0.8, right? It is 400 into 0.2, right? 400, this is Newton per meter, and this one is in meters, right? Say this is meter, then it is 80, right? 80 Newton, right? So you need 80 Newton force for this elongation, right? So if you have in particle equilibrium, if you have this type of elastic springs to support your particle, you can use this equation to find out the force in springs, right? So we'll see the examples in coming slides, then you will understand it more. The second type of supports is cables and pulleys. So in this course, throughout this course, we assume that all cables will have negligible weight and they cannot stretch. Okay, so we assume all cables have negligible weight and they cannot stretch, which means that if we take a cable, the length of the cable is fixed and it has a negligible weight, right? A cable can support only a tension or pulling force, and this always acts in the direction of the cable, right? So if we take a cable, if we take this is a cable, then it only have tension forces like this. There is no compression. We take if we assume this as a cable, then we say cable can support only tension forces, right? This is a tension forces. It can only support tension force, not compression forces like this, right? This type of no only support tension forces, and it always acts in the direction of the cable, right? So if this is the cable, it acts only in the direction of the cable, not around here, not in this direction, right? The force is always acts in the direction of the cable, right? The tension force developed in a continuous cable which passes over a frictionless pulley, right? Frictionless pulley must have a constant magnitude, right? So if you take this cable, the tension in here, if we assume as T, then here also the tension must be T, and here tension must be T, here the tension must be T. It must have a constant magnitude, okay? The magnitude of the tension force is constant, right? So here the magnitude of the tension is equal, right? If we assume this is a tension force is 100, then here also the magnitude is 100, but the direction might be changed, okay? That's why I tell it is a constant magnitude, right? So here also the magnitude is 100, but the direction is different, right? Here it is here in this direction, but here it is in this direction. Here also the magnitude should be 100, right? So if it is a continuous cable and it is going over a frictionless pulley, then it must have a constant magnitude, right? The tension force must should for magnitude of the tension force must be equal everywhere in the cable if it is a continuous cable, right? So in this course we are dealing with the frictionless pulleys only. We are not dealing with the friction pulleys with frictions, dealing with the frictionless pulleys without friction, right? So if a cable going through that type of a pulley, frictionless pulley, then we assume the magnitude of the tension force along the cable is equal everywhere, right? So the force might be different because force has a magnitude and the direction, but the magnitude of that force is equal, right? The last type of support is the smooth contact. If an object rests on a smooth surface without friction, right? Then the surface will exert a force on the object that is normal to the surface or perpendicular to the surface at the point of contact, right? So if we take this for example, here say this is a uh, disk, then there is a force acting on this along the cable is T, right? So there is another force here which acts in the vertical direction. We say it is MGOW, right? So now this one is our smooth contact, smooth surface. So according to this, it says that surface will exert a force on the object that is normal to the surface. So the contact point is here. The force is normal to the surface. So it should be in this direction, right? Normal to the surface. Phase at the point of contact. So the point of contact is here, right? So then force should be in this direction, right? It should normal to the surface. What you should remember is that force is normal to the surface or perpendicular to the surface, not perpendicular to the this object, but perpendicular to the surface, right? So if it is a smooth surface, which means that no friction, then the surface will exert a force on the object that is normal to the surface at the point of contact, right? So this is, say, R, right? So whenever you have this type of smooth surface, then the force exerted by this surface on the object is normal to the surface. So we have discussed three types of supports, right? First one is the spring, the second one is the cables and pulleys, the third one is the smooth contacts, right? So these type of supports will, when we are solving the uh, equilibrium of particle, this type of supports will come, right? So you should know how the forces are exerted by this type of supports, right? So I mentioned that particle to be in equilibrium, the resultant force acting on a particle should be equal to 0. Then only particle can be in equilibrium, right? So we want to find if some particle is said to be in equilibrium, then we want to find whether the resultant force acting on that particle is 0 or not, to check whether the particle is in equilibrium or not, right? If the resultant force acting on the particle is equal to 0, then we can say that particle is in equilibrium. If the resultant force acting on the particle is not equal to 0, then the particle is not in equilibrium, right? To find the resultant force acting on the particle, whether it is equal to 0 or not, we should apply the equation of equilibrium, right? So we must account all the known and unknown forces acting on the particle. So the best way to do this is to think of the particle as isolated or free from its surrounding. We say we remove all the supports that particle has and we isolate the particle from the surrounding. A drawing that shows the particle with all the forces that act on it is called the free body diagram, right? So we use free body diagram to apply the equation of equilibrium. We use the free body diagram to demonstrate all the forces acting on the particle. So we use that diagram to calculate whether the particle is in equilibrium or not. So now let's see how we can draw a free body diagram. So first step is you should draw the outline shape of the particle, right? So make the particle isolate or cut free from its surrounding. So which means that, say, if this is our example, so this steel, uh, so that say that this is a steel wheel which hangs using the cables at A and B, right? So if we want to draw the free body diagram of this, first thing that we should do is we should remove these two cables and make it isolated, right? And draw the outline shape of the steel, this is steel wheel, right? Then you should indicate all the forces that act on the particle, right? Indicate all the forces that act on the particle. So if you take this one, what are the forces acting on this steel wheel? You can see there is a cable, right? We learned that the cable, the force is along the cable, right? So there is a force in this direction, right? This is the point A, and there is another cable at point B. So there is another force at this direction, right? So then there is a mass. This wheel has a mass, so there is a weight of this wheel, right? So it is from the center of this wheel, right? We know, since this is a particle, to consider this as a particle, these three forces should meet at one point, right? So all these forces should meet at here, right? So then the third step is label the known forces with their proper magnitudes and directions, right? Use the letters to represent the magnitudes and direction of unknown forces, right? So if you don't know uh, the say that if these are unknown forces, we can use letters. Say this is the tension force, I use the T, and which applies at A, so I use the TA. This is a tension force which applies at point B, so I use the TP, right? So say if the mass of this wheel is 5 kilogram, then the weight of this one is 5 into 9.81, right? 5 g, right? So this is, we call the free body diagram, or this one we call as the free body diagram of this particle, right? So first thing, when you draw the free body diagram, is you should remove all the surrounding, or remove all the supports of that particle and get the particle isolated, right? Then second step is you should show all the known and unknown forces, right? Third step is you should label all the known and unknown forces. So you should label the known forces with their proper magnitudes and directions, and you can use the letters to represent the magnitudes and the direction of unknown forces, right? Say if somebody uh, use the direction, I use the direction in this side, if somebody use the direction of this side, if the force is unknown, it is still okay. If you apply the equilibrium equation, you will get the correct direction, right? So we'll look at that when we are discussing the examples, right? Okay, let's see some example how we can draw the free body diagram of a particle, right? In the example one, it says the sphere in figure has a mass of 6 kilogram, right? So this is the sphere in the figure which has a mass of 6 kilogram, right? And is supported as shown, right? So CE is a cable and ABC also a cable, and K, this one is the spring, right? So draw a free body diagram of the sphere, the chord CE, and the knot at C. Right? So we should draw free body diagram for the sphere and the chord and the knot. Right? So if we take the sphere first, what should we do when we need to draw the free body diagram? So first thing is that we should cut all these supports and take the sphere out, right? So we should draw the outline of the sphere, right? So we remove all the supports and draw the outline of the sphere. Then second step is we should draw all the known and unknown forces, right? So we know that mass of this sphere is 6 kilogram, right? So we know there is a force in this direction, right, which is equal to, it's a force in this direction which is equals to 6g, or 6 into 9.81, right? And since there are, this is a smooth contact, right? This is a smooth contact support, right? So in the smooth contact support, we learn that the force is perpendicular to the contact, the smooth surface, and acts where the object touches the smooth surface, right? So there is a force in this direction. Say that this is the smooth surface. There is a perpendicular force in this direction, and there is another smooth surface, right, which acts in this direction, which is perpendicular to the surface, right? Since this is perpendicular to the surface, right, so it should goes through the center of this sphere, right, because this is a tangential line, right? So these contacts are tangential lines to this sphere. So anything perpendicular to that tangential line which should go through the center of the sphere, right? So these forces we don't know the magnitude, right? But we can calculate the direction, right? So if we take this one is 30 degrees, right? So if you take this, okay, let's label this as N A and this as N B, right? There is another force from this cable, right? We know that cable, the force is along the cable, right? So there's another force in this direction which is in here, which should also go through this, right? So we can also label as T C E, right? So if you look at here, this is the free body diagram of the sphere, right? So you can see that this is the weight of the sphere, and this one is that force from this support, and this is the force from this support, and this is the force due to the cable or the cord CE, right? So this force, you know the direction and magnitude, so you mark the direction and magnitude. But for these forces, you don't know the magnitude, but you know the direction, because from here you know the direction, right? So here this angle is 30 degrees, right? So if we take this one is 60 degrees, so this one is 60, and so this angle is 30 degrees, right? So you should use that geometry to calculate the angle, right? So then this is the free body diagram of the sphere, right? So if you ask to draw the free body diagram of the chord, so you separate this chord CE, you take it out, right? You isolate it. Then what are the forces acting on this chord CE? There are two forces. One is from this sphere, which is in this direction, and one is at this point, so which is in this direction, right? So if you now take the knot at this point C, how many forces that act on this knot C? When you want to draw the free body diagram, you should separate the knot C out. So how many forces that act on? There are three forces, right? Which is one from this chord CE, another one from the chord BC, and other force is from this spring, right? So these are the three forces, right? All these are unknown forces, so you just label them accordingly with their directions, right? So this is how we draw the free body diagram for a particle, right? Okay, now let's discuss about how we can use equilibrium equations to solve particle equilibrium. First, we'll discuss about the particle is subjected to a coplanar forces. As I mentioned in our earlier slides, coplanar forces mean forces on the same plane, right? So forces on the same plane means it is a two-dimensional system, right? So if we have a particle and all the forces on that particles are coplanar, then we can say for equilibrium, for a particle to be in equilibrium, we know that the resultant force should be equal to 0, which means how we can derive the resultant force? We should take the vector summation of all the forces, right? So if we take the vector summation of all the forces, this is that equation, right? Vector summation of all the forces. This for F is a vector, right? So vector summation of all the forces on that particle should be equal to 0, right? So if we divide or resolve all these forces into two-dimensional axes x and y, we know the unit vector in x direction is I, unit vector in y direction is j, right? Then we can express this equation in other way as like this: fx, which means the forces in the x direction, resolvement of the forces on the particle in x direction times I plus sigma Fy times j, which means resolvement of all the forces in y direction is equal to 0, right? So if this equation is to be equal to 0, we know that sigma fx should separately equal to 0, sigma fy should separately equal to 0, right? So this is the equilibrium equation that we can use to solve the equilibrium of a particle, right? So if it is a coplanar system, if a particle should be in equilibrium, we know that our condition was the resultant force of the particle should be equal to 0. So we, starting from that, we can derive that if you resolve all the forces into x and y direction, we can say the components in the x direction should be equal to 0, and the components resolvement of the forces in the y direction, which means sigma Fy, should be equal to 0, right? So this is the vector summation of forces should be equal to 0, and here it is the algebraic summation. Okay, this is not the vector, here it is vector summation, but here it is the algebraic summation, right? So you should understand the difference, right? Vector summation, you should use the Cartesian notation I and j, but here you can just add the only the algebraic parts of the vector notation, right? So let's see how we can use our knowledge of equilibrium equations and free body diagram to the solve some problems, right? So first problem, it tells determine the tension in cables BA and BC necessary to support the 60 kilogram cylinder in figure, right? So this is the cylinder. So the weight, the mass of this cylinder is 60 kilogram, right? Since this one is hanging, we know that because of this 60 kilogram, these two cables are in a tension, right? So this system is in equilibrium, right? So now we need to determine the tension in this cable and tension in this cable, right? So how, let's see how we can solve this type of problems, right? So first is we, so if we take this cylinder, the weight, if we take this cylinder, we, let's first draw free body diagram for this cylinder, right? So if we take this cylinder as this, if I take like this cylinder as this, then we know weight is in this direction. Weight of this cylinder is 60. Weight of this cylinder is, weight of this cylinder is, this is 60 times 9.81, right? The mass of the cylinder is 60 kilogram. The weight is 60 times 9.81 Newton, right? So this cylinder equilibrium, there is another force in this direction due to the BD cable. So I represent that as, we know the direction, it is along the cable. So I represent this as TBD, right? It is a unknown force, right? So now we know, to this cylinder to be in equilibrium, we know that sigma F should be equal to 0. Also we know, if we consider this as our positive x direction and this as our positive y direction, then we know sigma fx should be equal to 0 and sigma fy should be equal to 0, right? It is the same equation, right? So we know the vector summation of, if some particle is to be in equilibrium, vector summation of the forces acting on the particle should be equal to 0. If we resolve that into x and y direction, we can say resolvement of the forces into x direction should be equal to 0. The resolvement of the summation of the resolvement in y direction should be equal to 0, right? So x direction, if we take this as x direction, there are no forces, right? So this condition satisfied, right? So if this cylinder to be in equilibrium, then we can say sigma Fy should be equal to 0, right? So what are the forces in y direction? We know it, TBD is in positive y direction. So say TBD, right? And this force in negative y direction, we say it is 60 times 9.81. Those are the force. Two forces should be equal to 0. From this we can find out the, we can say TBT is equal to 60 times, we can say TBT is equal to 60 times 9.81, 60 times 9.81 newtons, right? Newton, right? So this is the value of TBT, right? But now we want to find the tensions in this cable and this cable, right? That is what the question is asking, right? BA and BC cable, right? So how can we find the tensions in BA and BC cables? So if you take this ring, right? So if you consider the equilibrium of this ring, so this we can consider as a particle, because we don't need this dimension to find the, to write the equilibrium equations, right? So if we consider the ring B, we consider the uh, ring B, if we consider the ring B, we can say, we know that if this ring is to be in equilibrium, we know sigma Fx should be equal to 0 and sigma Fy should be equal to 0, right? And okay, if one is equal to 0 and other one is not equal to 0, which means that the particle is not in equilibrium. If the particle is to be in equilibrium, both sigma fx should be equal to 0 and sigma fy should be equal to 0, should be, must be satisfied, right? So then what are the forces? First we take the forces in x direction. Say this is, we take as positive x direction. What are the forces in positive x direction? If I say this as TC and this as TA, so then TC, so I can write TC, the x resolvement in the x direction is TC cos 45, right? So resolvement of this in x direction is TA. If I say this angle is theta, so this one is in negative x direction, right? So it should be minus TA cos theta, right? The first thing that you should draw the, I forgot to draw that, you should draw the free body diagram for ring B. So this is the ring, right? Ring B, free body diagram for the ring B. This is the free body diagram for ring B. What are the forces on ring B? We know that there is a force in this direction which is equal to TBD. We know TBD is 60 times 9.81, right? So there is another force in this direction which we designated it as TC, right? Angle is 45 degrees, and there is another force in this direction, right? So we designated as TA, and this angle theta, we can say from here cos theta is equal to, you can see here cos theta is equal to, if this is theta, cos theta is equal to 4, is equal to 4 over 5, and sin theta is equal to, sin theta is equal to 3 over 5, right? So if I were, then we can write the equilibrium equations, right? So Tc cos 45, right? Tc cos 45, we take here Tc cos 45 minus Ta cos theta should be equal to 0, right? So this force here, this force is perpendicular in y direction, right? So the resolvent in the x direction is 0, right? So in the x direction we have only two forces, Tc cos 45 and Ta cos theta, right? So we can say Tc cos 45 is equal to Ta cos theta, we know cos theta is equal to 4 over 5, right? So this is our first equation. Then we write the forces in y direction. I say this is the positive y direction, so sigma Fy is equal to 0, right? So what are the forces in y direction? If we take this force, what is the resolvent in y direction? Ta sin theta, right? And this one also in positive y direction, plus Tc sine 45. How about this force? This is in negative y direction, we say it is minus TVD, which is equal to 0, right? We know Ta sin theta is 3 over 5 plus Tc sin 45, we know it is square root of 2, is equal to TBD. We know value of the TBD is 60 times 9.81. So this is our second equation, right? So now we have two equations, right? Algebraic equations and two unknowns. So can we solve this problem? Yes, right? Two equations, two unknowns, so we can solve the problem, right? So if you solve this one, you will get Tc is equal to 476 newtons, and Ta 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 is equal to 420 newtons, right? So we'll get something like this, right? Okay, in this problem it says the 200 kilogram crate in figure is suspended using the ropes AB and AC, right? So this crate, the mass of the crate is 200 kilograms, right? So this is suspended using cable, the ropes AB and AC. So each rope can withstand a maximum force of 10 kilonewton before it breaks. So the ropes AP and rope AC can withstand a maximum force of 10 kilonewton. If it is larger than 10 kilonewton, these ropes are breaks down, right? Broken down, right? So if AB always remain horizontal, and we are asked to determine the smallest angle theta which the crate can be suspended before one of the ropes breaks down, right? So we need to determine this angle, right? So we are given three things, right? First, the question gave us the mass of the crate, and it says the maximum forces that these two ropes can withstand is 10 kilonewton. And question also say AB is always horizontal. So we are asked to find the smallest angle, right? So which rope reach 10 kilonewton force first? By looking at just looking at this figure, you cannot say which rope will reach the 10 kilonewton first, right? So first thing is that you should you should draw the free body diagrams, then write down the equilibrium equation, then only we can find out which force, the tension in which rope is larger. So first thing, so we'll start from this cable, right? So if you draw the free body diagram for this cable, right? So if you draw the free body diagram for this cable AD, the free body diagram, you draw the free body diagram for cable AP. Okay, let's draw the free body diagram for cable AB. AB free body diagram. If we take the free body diagram for cable AD actually, then if you take this cable, the tensions will be acts like this, right? And we know this one is 200 kilogram. So the weight of this one is in here, it is 200 into 9.81, right? So the tension, if we this as TAD and this is also TAD, right? So we can say TAD, tension in this cable, which is should be equal to 200 times 9.81, 200 times 9.81, which is 1962 newton, right? So the cable in AD, the tension in cable the rope AD is 1962, right? So if we draw the free body diagram for this ring at A, free body diagram for ring at A, first thing that you should remove all the supports, you should remove all this cable. So we have this ring A, right? So then there is a tension in this AB direction, right? So we can say there is a force in this direction. We can add as this as FAB, right? So there is another force in this direction, right? Due to this AD cable, I write it as FAD, which is equal to 1962. And there is another force in this direction, right, which is I designated as FAC, and I take this angle as theta, right? We don't know the angle, right? So this is the free body diagram for this ring, right? For this ring. So then if we write the equilibrium equations, then we can say, if we say this is our positive x direction and sigma fx should be equal to 0. If this system is in equilibrium, the ring at A should be in equilibrium, so sigma fx should be equal to 0 and sigma fy should be equal to 0, right? So sigma fx is equal to 0. What are the forces in x direction? I can write as FAB. This is the force in x direction. Question says that the AP always remains horizontal. So the force AB is always horizontal, right? And this force doesn't come in x direction. So we have another force FAC, which is in negative x direction. So we put the minus sign. We write FAC cos theta, which is equal to 0, right? From here we can say FAP is equal to FAC cos theta, right? So this is our first equation. Then we write the equation for positive y direction. We say this is y direction, so sigma fy should be equal to 0. I take this. Then what are the forces in y direction? FAB is a horizontal force which is in x direction, so it will not come. So we have FAC, can write as FAC sine theta, and FAD is in negative y direction, so FAD equal to 0. We know FAD force, right? So FAC is equal to 1962 divided by sine theta. So this is our second equation, right? So from this we have determined FAC and FAB, right? So which force is larger then? From equation 1, if we take the equation 1, can see FAB is equal to FAC cos theta, right? We know then theta is larger than 0 and greater less than 90 degrees, which means that cos theta is smaller than 1 and larger than 0. At cos 0 is 1, cos 90 is 0, right? So cos theta varies between 0 and 1, right? So we know from this that since cos theta is varies between 0 and 1, from here we can say, which means that cos theta, value of cos theta is somewhere like 0.9 or 0.8, 0.75, like that, right? So what can you say about the FAB and FAC force? If it is 0.9, FAB is equal to 0.9 times FAC, which means FAC force is larger than FAB. If it is point 0.8, FAB is equal to 0.8 times FAC. So we can say in generally FAP is less than FAC, right? So we can say FAC force is larger than, always greater than the FAB force, right? Do you understand that part? So we know, so FAC is always greater than FAP. So which means that FAC reach 10,000 or 10 kilonewton first than FAB, right? So when FAB reach 10 kilonewton, FAC is, since FAC is larger than FAB, the value of FAC is larger than 10 kilonewton, right? If this ropes to not to be broken, then FAC should be equal to 10 kilonewton. At that time FAB is smaller than 10 kilonewton, right? So we need to find the angle where, smallest angle where these ropes are not to be broken, right? So then we can say, we can substitute from second equation, we can say, we can substitute the value of FAC as 10,000 or 10 kilonewton is equal to 62 divided by sine theta, right? So from here you can find out the value of theta. Sine theta is equal to 1962 divided by 10,000. So theta is equal to sine inverse uh, 0.1962, which is equal to 11.3 degrees, right? So this is the smallest angle that this system can take before breaking the system, right? So if you want, you can find out the the AB force also. FAB is equal to, from our first equation, FAB is equal to FAC cos theta, right? So FAC is now 10,000 Newton, FAC cos 11.3 degrees, right? So we'll get which is equal to 9 Newton, right? So when the FAC reached 10 kilonewton, the value of FAB is 9.81 kilonewtons, right? So this is how we solve this type of problem, right? So we have discussed about the two-dimensional force systems or equilibrium of a particle which is subjected to coplanar forces, right? So now we are going to discuss about the three-dimensional force systems or particle which is subject, equilibrium of a particle which is subjected to forces in three-dimensional system, right? So it is merely the extension of our the two-dimensional one. The condition for the equilibrium doesn't change, which remains as original, which means that the vector summation of all the forces acting on the particle should be equal to 0, which means that sigma f in our first equation, this equation, right? The sigma f should be equal to 0. This is the vector f. So this summation means vector summation, right? Since we have now 3 dimensions, so we can write it like this, right? Sigma fx times I plus sigma fy times j plus sigma fz times k should be equal to 0. I, j and k are unit vectors along x, y and z directions, right? If this equations to be satisfied, or each of these components should be equal to 0, which means the summation, algebraic summation of sigma, the the forces in x direction should be equal to 0. Algebraic summation of the forces in y direction should be equal to 0, and the algebraic summation of forces in z direction should be equal to 0, right? So in the case of the coplanar forces, we have only these two, right? In the case of the particle which is subjected to forces in 3 dimension, we should consider all x and y and z directions, right? So this is the equilibrium equation that you can use to solve problem which is in 3 dimensional system. Okay, 90 kilogram load is suspended from the hook shown in figure, right? So 90 kilogram of weight is suspended using this hook. If the load is supported by two cables AD and AC and a spring AB, the spring stiffness constant K is equal to 500 newtons per meter. So we are asked to determine the force in cable AD, AC and stretch of the spring for equilibrium. Cable AD lies in the XY plane. Cable AC lies in the XC plane, right? So AD lies in the XY plane means that force on the cable AD can only be resolved into X and Y direction. The component in Z direction is equal to 0. Cable AC lies in the XZ plane means you can resolve the tension force in the cable AC into X and Z direction. The component in the Y direction is equal to 0, right? And the spring K, spring AP is on the Y direction, right? So now we need to find what are the tension in AD cable, AC cable and the stretch of the spring, right? So how can we solve this type of problem? Uh, if you want to find the tension in these two cables and the force in this spring, you should draw the free body diagram for the ring at A, right? So if we consider the point A, say this is the ring, there is a force in this direction, right? So we have force in this direction. Then we can call it as, you can call it anyway, but I call it as a FAD, right? So there is a force in this direction which is equal to 90 times 9.81, right? So this angle is equal to 30 degrees, right? This force is on XY plane, right? So there is a force in y direction which I call as FAP, right, which is in the y direction, and there is a force in this direction also which I call as FAC, right. So this angle is theta. You can see this is 4, 3 and 5, right. So now we have drawn the free body diagram. We have marked all the unknown and known forces with their directions, right. Now we know that this is the particle in equilibrium subjected to forces in three system, right. So this particle to be in equilibrium, we know sigma fx should be equal to 0, sigma fy should be equal to 0, and sigma fz should be equal to 0, right. So if we take the forces in x direction, I say this direction is positive, so we can say sigma fx is equal to 0. So if I write the equations in the x direction, this force is on xy plane, so the resolvement count, the resolvement in the x direction, it is in positive x direction, right. I can write as f a t sine 30, right. And this force, it is in z axis, so no resolvement in x direction. This one, no resolvement again in x direction as it is on the y axis. How about here, it is on the xz plane, so it comes, right. So minus FAC, if I take this angle as theta, so FAC cos theta, right, FAC cos theta, cos theta is equal to, you can see this angle is theta, 4 over 5, right. So I can write, if I delete this cos theta, I can write as 4 over 5, right. FAD sine 30 minus FAC times 4 over 5 is equal to 0, right. So if I take this as my positive y direction, you should always mark which direction is positive, right. If I mark this as my positive y direction, then I can write as FAP, which is the force in y direction, right, minus, if you take this one, this force which is in negative y direction, FAT cos 30 is equal to 0, right. So this is my first equation, this is my second equation, right. So if I take the z direction, if I take this as my positive z direction, what are the forces in positive z direction? We have this force is in negative y direction, right. So minus 90 into 9.81, right. And we have the resolvement of this force, which is plus FAC sine theta is equal to 0, right. We know sine theta is equal to 3 over 5, right. So I can say, if I delete this sine theta, FAC times 3 over 5 is equal to 0, right. So this is my third equation, right. So from this you can say, so from the equation 3 you can find FAC FAC times 3 over 5 is equal to 882.9. So you can find FAC from that, right? So if you know the FAC from equation 1, if you know the FAC from equation 1, you can find the value of FAD, right? So if you know the FAD, you can find the value of from equation 2, you can find the value of FAB, right? So you can find the tensions in AD cable and AZ cable, and now we need to find the stretch in the spring, right? So we have found the force FAB. We know F is equal to K times S, right? So we know FAB force, we know the value, and we know the stiffness constant in 500. So then we can find the stretch S, right? So we'll get the value for S, right? So likewise, we can solve particles which is in equilibrium by subjecting to forces in three-dimensional system, right?